we'll understand logic gates. Logic gates perform logical operations. So they will perform logical operations. These logical operations are performed on one or more binary inputs and it will produce single binary output. So operations will be performed on one or more than one input and output will be only one output. We can classify logic gates as basic gates, universal gates and special gates. First let us see the basic gates. Basic gates perform basic Boolean operations. So the basic gates will perform basic Boolean operations. So the basic Boolean operations are AND operation, OR operation and NOT operation. So they will perform basic Boolean operation like AND operation, OR operation and NOT operation. So based on these basic Boolean operation, we can classify basic gates as AND gate, OR gate and NOT gate. First let us see what is an AND gate. So this is the symbol for AND gate. It will be having two inputs A, B and output will be A dot B. So if we write the truth table, so if we take two variables A, B, we will be having four combinations 0, 0, 0, 1, 1, 0, 1, 1. So if we write output for this, y is equal to A dot B. AND operation is similar to the multiplication operation. Here the gate will consider both the inputs to produce the logical output. So if we multiply 0 and 0, it will be 0. So the operation 0 and 0 will be 0, 0 and 1 will be 0, 1 and 0 will also be 0, 1 and 1 will be 1. Now let us take OR gate. This is the symbol for OR gate. So it will be having two input A, B. It will be having one output. So we can write it as A plus B. So if we write the truth table, there are two inputs A, B. It is having one output y is equal to A plus B. So two variables, four combinations of input will be there 0, 0, 0, 1, 1, 0, 1, 1. So OR gate will perform operation similar to addition. 0 or 0 is 0, 0 or 1. So the OR gate will choose 1. So output will be 1. 1 or 0, here OR gate will choose the best option which is 1 and 1 or 1. So OR gate don't have any option. So both are high itself. So output will be 1. Now let us see NOT gate. This is the symbol for NOT gate. So it is having only one input and one output. So input is only 1 and one output. So here the output of NOT gate is complement of the input, or we can say negation of the input. So if the input is 0, output will be 1, and if the input is 1, output will be 0. Now let us understand universal gates. The name universal gates because any Boolean expression can be implemented using these gates. So we can implement any Boolean function or any Boolean expression can be implemented using these gates. That's why they are known as universal gates. So we can implement any Boolean expression or any Boolean function using these gates without using any other logic gates. So other logic gates are not required. Only using these gates we can implement any Boolean function. That's why the name universal gates. So there are two universal gates. First one is NAND gate and second one is NOR gate. First let us see the NAND gate. AND gate plus NOT gate is NAND gate. So if we take a AND gate with two inputs A, B, output of this AND gate, if we connect a NOT gate, the resulting gate is known as NAND gate. So Y will be equal to AND gate output will be A dot B, and due to this NOT gate we will get output as A dot B whole bar. This is the symbol of NAND gate. So write an AND gate, at the output put a bubble, and it is having two inputs A, B, one output Y is equal to A, B bar. So complement of AND gate is NAND gate. So two variables are there, A, B, and output of NAND gate is Y is equal to A, B bar. So two variables, four combinations of input 0, 0, 0, 1, 1, 0, 1, 1. So 0 and 0 is 0. So complement of 0 is 1. 0 and 1 is 0. Complement of 0 is 1. So 1 and 0 is 0. Complement of 0 is 1. 1 and 1 is 1. Complement of 1 is 0. So this is the truth table for NAND gate. Now let us see NOR gate. OR gate plus NOT gate will give us NOR gate. So if we take an OR gate with two inputs A, B, output of the OR gate, if we connect NOT gate, the output will be A plus B whole bar. So this is the operation of NOR gate. So where it is taking the complement of OR operation. So writing the symbol of NOR gate. So write a OR gate, at the output put a bubble, it will be a NOR gate. So it is A, B, output is equal to A plus B whole bar. Complement of OR operation is NOR operation. Now let us write the truth table by taking two inputs A, B, and output Y is equal to A plus B whole bar. So two variables, four combinations of input will be there, 0, 0, 0, 1, 1, 0, 1, 1. 0 or 0 is 0. So complement of 0 is 1. 0 or 1 is 1. Complement of 1 is 0. 1 or 0 is 1. Complement of 1 is 0. 1 or 1 is 1. Complement of 1 is 0. So this is about universal gates. Now let us see special gates. So there are two special gates. First one is XOR gate and the second one is XNOR gate. This is the symbol for XOR gate with two inputs A, B, and output is written as A. We'll write plus sign with a circle that specifies XOR operation, and B, Y is equal to A XOR B is the output of XOR gate. Now let us write the truth table. Let us take two variables A and B, and output is A XOR B. Two variables, four combinations of input 0, 0, 0, 1, 1, 0, 1, 1. So XOR gate is a logic gate that will produce output as 0 when inputs are same. So if the inputs are same like 0, 0 and 1, 1, so output will be 0. If inputs are different like 0, 1, 1, 0, output will be 1. So from this we can write the expression as Y is equal to, we need to consider where we are getting output as 1, and we can write the expression A bar B plus A B bar. So this is written as A XOR B. Now let us see XNOR gate. So the symbol for XNOR gate is like this. So this is the symbol for XNOR gate. So similar to XOR gate, we'll write at the output, we'll write one bubble A, B, Y is equal to A, we'll write a dot and a circle that specifies XNOR operation B. So Y is equal to A XNOR B. So we'll write the truth table for this. A, B, Y is equal to A XNOR B. There are two inputs. There will be four combinations of input: 0 0, 0 1, 1 0, 1 1. Now XNOR gate is a logic gate that will produce output as 1 when inputs are same, and it will produce output as 0 when input are different. So we are having input as 0 0, so output will be 1, input as 1 1, output as 1, so output will be 1 when inputs are same. So when the inputs are different, output will be 0. So from this we can write the logical expression for XNOR gate. So Y is equal to, so here we are getting 1, so we can write it as A bar B bar plus, here we are getting 1, so we can write this as A B, so which is A XNOR B. So from this truth table itself, we can identify if we take the complement of XNOR gate. So A XNOR B complement is nothing but your A XOR B, and it is vice versa. If we take complement of A XOR B, it will be A XNOR B, and if we take complement of A XNOR B, it will be A XOR B. So this is about special gates.
Now let us understand the implementation of basic gates using universal gates.
So we know there are three basic gates: NOT gate, AND gate and OR gate. We will implement these three basic gates using universal gates, which are NAND gate and NOR gate. We know NAND gate and NOR gate are known as universal gates. Now let us implement basic gates using NAND gate. We know the expression for NAND gate. It is A dot B whole bar. So always remember, while implementing any Boolean expression using NAND gate, we need to eliminate plus sign. So in a Boolean expression, if there is plus sign, so we need to eliminate this plus sign. We need to eliminate this plus sign, which means we need to eliminate OR operation. So you need to always remember this. So if you do this, you can easily implement any Boolean expression using NAND gate. First let us take NOT gate. So this is the symbol for NOT gate. So we know if we give input as A, output will be A bar. Negation of A will be the output. So we will get output as A bar. So here Y will be equal to A bar. Now let us implement this expression using NAND gate. So let us take a NAND gate. We know NOT gate is having only one input, so that's why we'll short the two inputs of NAND gate and we'll make that as one input, and we'll give input as A. For both the terminals, input is A, so output will be A dot A whole bar. So we know from De Morgan's theorem, we can write this as A bar plus A bar. So we know that A plus A is nothing but A. So using the same analysis, we can write this equation as A bar. So we have implemented a NOT gate using only NAND gate. Now let us take an AND gate. Let us write the symbol for AND gate. So input is A, B, output will be Y is equal to A dot B. So this expression we need to implement using only NAND gate. So let us take a NAND gate. Let us write two inputs A, B. So if the inputs are A and B, so output of NAND gate will be A dot B whole bar. So output will be A dot B whole bar. Now we require only a dot b, so we don't require this complement. So to eliminate this complement, we can connect a NOT gate using NAND gate. So let us connect a NOT gate to the output of this. So we know the output of NOT gate is complement of the input. So if the input is a dot b whole bar, output will be a dot b bar, and we'll get one more bar due to this NOT gate. So what happens? So here this double bar will cancel out and we'll get the equation as a dot b. Now let us implement OR gate using NAND gate. So this is the symbol of OR gate. Input will be AB, output of OR gate will be y is equal to a plus b. We know that to implement any given expression using NAND gate, we need to eliminate plus sign. So we are having a plus sign here. We need to eliminate this plus sign. So what we can do? So we can write down the same equation a plus b, and we can apply double bar for this equation, because we know a can be written as a double bar. So in the same way, a plus b can be written as a plus b double bar. So what we can do is, so we can simplify this inner bar using De Morgan's analysis. We know that a plus b whole bar can be written as a bar dot b bar. So using this analysis, we will simplify this. So we will get the equation as a bar dot b bar whole bar. So we have simplified only the inner bar and we have retained the outer bar. So the given expression is reduced to a bar dot b bar whole bar, and we have simplified this using De Morgan's theorem. Now it is easy to implement this expression using NAND gate. So what we can do? First let us implement a bar, then we can implement b bar. So this will be first term dot second term whole bar. So this is similar to NAND operation. So we can easily implement this using NAND gate. So first let us implement a bar using NOT gate. This is a, output will be a bar. So now let us implement b bar using NAND gate. So let us use NOT gate to get b bar. So we got a bar and b bar. So first term dot second term whole bar is one more NAND operation. So we can use one more NAND gate. So output of this NAND gate will be, this is the first term a bar, this is the second term. So it will be first term dot second term whole bar. So it is a bar dot b bar whole bar. So this is nothing but a plus b. So we have implemented all the basic gates using only NAND gate. Hope you understood this topic. Now let us implement basic gates using NOR gate. NOR gate will be in the form of a plus b whole bar. So this is the expression for NOR gate. So always remember, to implement any given Boolean expression using NOR gate, we need to eliminate dot sign. So this sign should be eliminated. Let us implement three basic gates using only NOR gate. So first let us start with NOT gate. So this is the symbol for NOT gate. If input is a, output will be y is equal to a bar. So let us implement this expression using only NOR gate. So let us take a NOR gate. Since NOT gate is having only one input, so we can short two inputs of NOR gate and make it as one input. So we will give input as a. So for both the input terminals, input will be a. So output will be a plus a whole bar. Using De Morgan's theorem, we can simplify this as a bar dot a bar. So we know a dot a is nothing but a. Using the same analysis, we can write this expression as A bar. Next we will implement AND gate. So this is the symbol for AND gate. So it is having two inputs A, B. Output of AND gate is A dot B. To implement this expression, as you can see in this expression we are having AND operation. So dot sign we need to eliminate to implement any given expression using NOR gate. So what we will do, so we'll write down the same expression A dot B and we'll apply whole double bar. So we know A double bar is nothing but A. Using the same analysis we have written this expression A dot B whole double bar is nothing but A dot B. We'll simplify the inner bar and we'll retain the outer bar. So we know from the De Morgan's theorem A dot B whole bar can be written as A bar plus B bar. So using the same analysis we will write this expression as A bar plus B bar whole bar. Now it is easy for us to implement this expression. So we can implement A bar first and we can take that as one term, and we can implement B bar and we can take that as another term. So first term plus second term whole bar is nothing but NOR operation. So first let us implement A bar using NOT gate. So let us take a NOR gate and implement a NOT gate. So input is A, output will be A bar. We'll take one more NOT gate using NOR gate. We'll take B as input and output will be B bar. So we got A bar and B bar. So this is first term plus second term whole bar, that is one NOR operation. So that's why we'll use one more NOR gate and the output will be A bar plus B bar whole bar. So first term plus second term whole bar is NOR operation. So we got this as A bar plus B bar whole bar, so which is same as A dot B. So we have implemented AND gate using only NOR gate. Next we will see OR gate. So this is the symbol for OR gate. So two input A and B, output will be A plus B. So let us take a NOR gate with two inputs A, B, A, B. So output of this NOR gate will be A plus B whole bar. So as you can observe from this equation we got A plus B whole bar. So but we require only A plus B. So what we can do, we can complement this term to get A plus B. So to complement this term we can use a NOT gate at the output. So at the output use a NOT gate. So we will get the complement of this term. So which means we will get A plus B bar. So this term, so due to NOT gate we will get one more bar. So double bar will cancel out and we will be left out with only A plus B. So we will be left out with only A plus B. So this is from the analysis A double bar is nothing but A. So using the same analysis we can write A plus B whole double bar is nothing but A plus B. Hope you have understood this topic.
Now let us understand implementation of XOR gate and XNOR gate using universal gates.
NAND gate and NOR gate are known as universal gate because any given Boolean expression can be implemented using these gates. Now let us see XOR gate implementation using universal gate. Now let us implement XOR gate using NAND gate. We know the expression for NAND gate is A dot B whole bar, and always remember to implement any Boolean expression using NAND gate, always we need to eliminate plus sign in a given Boolean expressions. So we need to eliminate OR operation, or you need to remember we need to eliminate plus sign. So if you remember this, so you can implement any given Boolean expression using NAND gate. So this is very important, you need to remember. Now the expression for XOR gate is y is equal to a bar b plus a b bar. Now this expression is to be implemented using a NAND gate. So what we will do, so you can see in this expression we are having a plus sign, so we need to eliminate this plus sign. So we can rewrite the above expression as a bar b plus a b bar whole double bar, because we know that a double bar is nothing but a. So if we apply double bar, it will not change the above expression. Now we will simplify the inner bar and outer bar will retain as it is. So we will simplify the inner bar using De Morgan's theorem. So we know from De Morgan's theorem a plus b whole bar can be written as a bar dot b bar. So using the same analysis we can write a bar b whole bar dot a b bar whole bar, and we'll write one more outer bar which we have not simplified. Now this expression can be easily implemented using NAND gate. So you can see we can implement a bar first, then we can take b and we can implement that using one NAND gate, a bar dot b whole bar, that is one NAND operation. Next we can implement a, then we can implement b bar. So a dot b bar whole bar, that is one NAND operation. First let us do that. Let us implement this a bar. So using only NAND gate, so use a NAND gate. We can implement a bar using a NOT gate. So let us take a. Output of this NOT gate using NAND gate is a bar. So next term is b. So we will write as it is b. So these two inputs will be connected to a NAND gate. So output of this NAND gate will be a bar dot b whole bar. So we got this term. So we got this entire term. Now let us implement the second term. So we need to take a as it is, and for b we will use a NOT gate using NAND gate. So a b. So output of this NOT gate will be b bar. So these two inputs will be connected to a. So you can see a dot b whole bar is nothing but NAND operation. So let us connect it to NAND gate. So output of this will be a dot b bar whole bar. Now we got this entire term and we got this entire term. So from this we can see first term dot second term whole bar is another NAND operation. So we can write one more NAND gate by connecting these two inputs. So the output of this NAND gate will be a bar b whole bar dot a b bar whole bar and one more bar for this NAND operation. So this expression is same as a bar b plus a b bar. So we have implemented XOR gate using only NAND gate. Now let us implement XOR gate using NOR gate. So NOR operation is a plus b whole bar. So always remember, to implement any given Boolean expression using NOR gate, we need to eliminate dot operation. So AND operation we need to eliminate. So if you remember this, you can implement any given Boolean expression using NOR gate. Now let us write the expression for XOR gate. So y is equal to a bar b plus a b bar. So you can see we are having an AND operation between a bar b. So a bar dot b, and we are having an AND operation between a dot b bar. So we need to eliminate these two. So what we will do, we will apply individual whole bar. So let us write the above equation, a bar b plus a b bar. So we will apply individual whole bar. So this will not change the given expression. Now let us simplify this. So we'll simplify only the inner bar and we'll retain the outer bar as it is. So if we simplify the inner bar using De Morgan's theorem, so it is A double bar plus B bar whole bar plus A bar plus B double bar whole bar. Now we can write this expression as A plus B bar whole bar plus A bar plus B whole bar. Now it is easy for us to implement this using NOR gate. So let us take A, then we will take B bar using a NOT gate. Let us implement that. So it is B, output of this NOT gate using NOR gate will be B bar. So these two inputs are connected to a NOR gate. So output of this will be A plus B bar whole bar. So we got this first term. Now let us implement the second term. So we will take a NOT gate to implement A bar. So A, output of this will be A bar. We will take B and we will give this input to a NOR gate. So output of this NOR gate will be A bar plus B whole bar. Now to get this OR operation, we will connect one more NOR gate. We will connect one more NOR gate. So output of this NOR gate will be this term plus this term whole bar. So we will write the first term, which is A plus B bar whole bar plus A bar plus B whole bar, and we got this first term plus second term whole bar. This is the output of this NOR gate. So if we observe the output, so we need to get this term, but we are getting the complement of this term. So what we need to do, we need to take the complement of this term to get the final output. So we will connect a NOT gate here using a NOR gate to eliminate that bar. So to eliminate whole bar, we will connect a NOT gate. So after connecting that NOT gate, we will get the output as A plus B bar whole bar plus A bar plus B whole bar and whole bar. Due to this NOT gate, we will get one more bar. So these two whole bar will cancel out. So we will be left out with the equation A plus B bar whole bar plus A bar plus B whole bar. So this equation is same as what we have simplified. So this equation is same as A bar B plus A B bar. So A bar B plus A B bar. So we have implemented XOR gate using NOR gate. Hope you have understood this topic. Now let us understand XNOR gate implementation using universal gate. So first let us implement XNOR gate using NAND gate. So always remember, to implement any given Boolean expression using NAND gate, you need to eliminate plus sign. So plus sign should be eliminated. So we need to eliminate plus sign to implement any given Boolean expression using NAND gate. Now let us write the expression for XNOR gate. So y is equal to A bar B bar plus AB is the Boolean expression for XNOR gate. Now we need to eliminate this plus sign to implement this expression using NAND gate. So let us eliminate this plus sign. So let us write the above equation A bar B bar plus AB whole double bar. So we know that A double bar is same as A. So using the same analysis, we can write A bar B bar plus AB whole double bar is same as above expression. So let us simplify the inner bar. So let us simplify only the inner bar and we will retain outer bar as it is. So we can write the above expression as So if we simplify this using De Morgan's theorem, so we can write this as A bar B bar whole bar dot A B bar and one more bar which we have not simplified. So we have simplified this using De Morgan's theorem, A plus B whole bar, which can be written as A bar dot B bar. So now let us implement this first term, which is A bar B bar whole bar. First let us implement A bar, then let us implement B bar. So A bar we can implement using a NOT gate, which is implemented using NAND gate. A output will be A bar. So we require B bar. We will take a NAND gate. B output of this NAND gate will be B bar. So A bar dot B bar whole bar is one NAND operation. So this entire term is one NAND operation. So we can use one more NAND gate to implement this. So output of this NAND gate will be A bar dot B bar whole bar. So we got this term. So let us implement the second term, which is a simple NAND operation, which is A dot B whole bar. So you need to take A, take B. So connect this input to A and B, connect this input to NAND gate. So output of this will be A dot B whole bar. Now we got this second term. So what we need to do? So you can see, so we got the first term, we got the second term. First term dot second term whole bar is one more NAND operation. So let us write one more NAND gate, and the output of this NAND gate will be first term dot second term whole bar. So let us write the first term, A bar B bar whole bar dot second term A B bar whole bar. So we got the same expression. So this expression is same as A bar B bar plus AB. So you can see this expression is same as A bar B bar plus AB. So we have implemented XNOR gate using only NAND gate. Now let us implement XNOR gate using NOR gate. So let us write the equation for the XNOR gate, which is y is equal to A bar B bar plus AB. Now to implement any given expression using NOR gate, we need to eliminate dot operation, which is AND operation. We need to eliminate dot function. So if you remember this, you can implement any given Boolean expression using NOR gate. So in this expression, we are having AND operation between A bar B bar, and we are having AND operation between A B. So we'll write down the expression A bar B bar plus A B. So we'll apply individual bar so that we need to eliminate AND function. So this will not change the above expression. So now let us simplify only the inner bar. So we'll retain the outer bar. We'll just simplify the inner bar and we'll retain the outer bar as it is. We know from De Morgan's theorem, we can write A dot B whole bar as A bar plus B bar. So in the same analysis, we can write A double bar plus B double bar whole bar plus A bar plus B bar whole bar. So we can write this expression as A double bar, we can write it as A plus B double bar, we can write it as B, A plus B whole bar plus A bar plus B bar whole bar. Now we can easily implement this function using NOR gate. Now let us implement the first term, which is A plus B whole bar, which is a simple NOR operation. So take a NOR gate, you take input as A B, output will be A plus B whole bar. Now let us implement the second term. So here we are having A bar and B bar. Let us implement A bar B bar first by using a NOT gate. Using NOR gate, A bar, let us implement B bar, it is B bar. So this term, we got a bar, we got b bar. So a bar plus b bar whole bar is NOR operation. So connect this to a NOR gate. So output will be a bar plus b bar whole bar. Now we have implemented this term, first term, and we have implemented the second term. So in between we are having a plus operation. So let us perform NOR operation for this. So let us implement a NOR gate here. So the output of this will be first term plus second term whole bar. Let us write the first term, which is a plus b bar, plus second term, which is a bar plus b bar whole bar, and whole bar due to this NOR operation. So you can see this expression is complement of the expression which we have derived. So to get the complement of this expression, we need to connect a NOT gate at the output. So if we connect the NOT gate at the output, so we'll get the complement of this term. So this will be a plus b whole bar plus a bar plus b bar whole bar. So this is the term, and due to this NOT gate we will get one more bar. So these two whole bars will cancel out. So we will get a plus b whole bar plus a bar plus b bar whole bar. So this is same as the expression which we have simplified. This expression is same as a bar b bar plus ab, which is XNOR operation. So we have implemented a XNOR gate using only NOR gate.
Hope you have understood these topics. Subscribe for more videos.